Thank you very much.
Yeah, and sorry for being late this morning. The pilot refused to land in London City because of fog this morning. First, I'll actually try to set the stage for sort of direction we have taken. The slide here is going to be extremely well known to you and boring, so I'll do them really fast. And then I'll take you into sort of our sort of part of it is our intervention technologies and our approach to interventions. And of course, we got depleting extremely fast, and all this is extremely well known to all of you. And that's actually sort of my background for when I started sort of my master thesis at university and actually worked on this idea. It was actually these sort of and nothing has actually changed since. Another thing that hasn't changed either is actually we're looking at still 40 years plus of production, so nothing has really changed that much either, and oil demand is still increasing. Interesting part here is that we have a sort of what actually the blue one looks like a production declining curve. And one of my sort of key ideas back sort of 20 years ago was actually what about utilizing the oil you already found in a more efficient way, and of course kind of that's sort of the traditional sort of probably Scandinavian way of looking at things, kind of how can we use things more efficiently, how can we save some labor time, or how can we make more efficient processes somehow. And today, kind of the industry has realized that you need to get every drop out of every reservoir, and probably average recovery rate around the world is probably 25% at this point in time. And there's a good reason for actually recovering quite a bit more out of that oil. Industry here is a bit sort of, unfortunately, a bit sort of slow to adopt new technologies. In the last sort of 30 years, the industry has changed quite a bit from the traditional sort of only vertical wells into different types of wells, extended reach, horizontal wells to a very large extent actually. And this is sort of where we come into play here. We build small robotic devices for intervention purposes, and the entire idea behind this is actually to increase recovery rates. So we have a large variety of tools where we can intervene into wells and actually repair them. A bit like the picture before, where you saw the picture from a hospital where heart surgery used to be open heart surgery. Today it's done by sort of small robotic devices, and actually it's exactly the same approach here, where we try to have the minimum impact on the patient as possible and achieve the same thing, just more faster, more efficient, and with less impact. So story back sort of 25 years ago actually, first ideas, and then it moved on, tool after tool. So today we've got a sort of entire portfolio of tools where we can address these different challenges with. And today we sort of have bases in most sort of districts around the world. And what we typically face is actually very simple issues, is scale. If you produce an oil well for more than 3 years or something, you typically end up in having simple issues like scale, sand, water problem, gas, corrosion. A lot of things that actually has to do with actually the conduit to surface. It has nothing really to do with the reservoir as such, but it's more to the fluid conduit heading up to the platform. So the question is, how do we maximize this and get the best out of it? This one here is actually from Statoil's own homepage, and it's no secret that the company was actually founded on the sponsorship from Statoil in Norway, where they were facing this production decline here back in the early 90s. And they were very keen on sort of finding ways of actually increasing their recovery rates. And what you can see today is actually more oil in that system is actually being produced from interventions compared to new wells. So a dramatic change within the last sort of 10 years. And this is just one example from one field in Norway, where you actually see sort of the January production, and then you see the year as it progresses, and you actually see kind of doing nothing, the grey one, then the yellow one doing interventions, and then green on top adding new wells into the same reservoir. And what you actually see here is then, as the year passes by, almost half the oil production is actually derived from intervention, optimizing, continuously optimizing. And it's who has sort of who should you give the credit for is actually is our tools or something else, but actually we are facilitating the ability to measure, to actually see that the process you have put into place actually works, that your fluid conduit to surface works, that all the things you have sort of imagined should work in your process is actually working. Here you see our sort of introduction of our technology in the Statoil system back in '96. Back then, the number of interventions were actually quite limited. It was done by relatively heavy equipment. And of course, one of the key elements here was also to get sort of a number of people on the platforms reduced, safer working environments, safer well conditions, and all that sort of combined with increased oil recovery. So what happened sort of during the first sort of 5 to 6 years was we had sort of our first sort of conveyance techniques, our first sort of simple jobs task, and then in 2003, 2004, we introduced actually more services, and number of jobs increased, and not did we only displace sort of older technologies, but we actually increased the market more, tripled the number of interventions. The blue one here stands for riser-less light well interventions. It's the same technology as the green one with tractors. It just means that instead of using a riser for intervening a subsea well, it's done with wire through water, so no riser to surface. And no riser to surface actually means it's actually an underbalanced operation. A bit like a sort of keyhole surgery, a heart surgery with robotics. You are not sort of changing any sort of pressures in the system. So you actually utilize the natural flow in the well to actually achieve the task set in front of you. So scale, for instance, scale milling, if that's sort of the case here, scale milling is actually done in a live reservoir with no fluid invasion, no introduction of any fluid. So actually the flow in the reservoir is maintained, but still optimized. And of course the idea was to work away from heavy interventions into as light as possible. And in terms of riser-less on subsea interventions, we actually done the job on, so far the depth record is 900 meters wire through water. And if you look at sort of the work scope we can actually perform on wire through water, we're actually looking at something like 90 to 95% of all well workover work can actually be conducted on wireline. And that is a huge difference, because once you don't need to have hydrocarbons coming to surface, you don't have to have water in your sort of riser system, it becomes a completely different story. The setup here is sort of you can intervene address a problem literally within hours and actually repair the well, either open a valve, close a valve, mill out a valve, remove scale. And sort of historically we actually started in the horizontal scene, where most of our jobs was conveying tools, measurement tools in horizontal sections. But today a lot of our work is actually removal of scale, downhole safety valves. Again, it's a simple issue, but downhole safety valves have to work, so of course it has to be fixed. Scale removal further down, valves that for some reason doesn't work anymore, override sort of smart completion to have stock systems in place. And of course a large part of our work is perforating, moving the production zone, reperforate, plug setting, straddle packers, so all the simple stuff that you sort of have heard about for many years is all possible on wireline, despite its vertical or through the subsea system. So this is sort of the type of issues we solve, and the amount of issues you can get with wells are quite enormous. So everything from perforating, well diagnostics to milling, you name it. And one of the key elements in our technology is how to deal with uncertainty, because obviously one of the things that we face when we plan an intervention, we have a lot of sort of uncertainty on actually what is the real problem. And the same sort of applies to actually the reservoir. It's a bit sort of like landing in heavy fork here, because when you begin sort of to drain your reservoir, you don't have all your parameters. It's a best guess, but as time progresses, sort of the knowledge base will increase, and you can actually make sort of a facts-based decision if you have enough facts in place. Another sort of theme here is actually where do we put the smartness? Obviously, kind of our philosophy has been that you put the smartness in the robots instead of putting the smartness in the hardware in the wells. And the idea is that robots can be retrieved to surface. You can build new generations of robots, increase their features, where the hardware in the ground is difficult to change. It's expensive. It's expensive to put into the ground, and if you put a lot of expensive jewelry in the ground from day one, you better be sure that you put the well in the right place, in the right sort of zone in the reservoir, and you have to be very sort of critical about sort of your initial sort of reservoir studies, where if you take a slightly different approach, where you say it's better that we take a learning approach, we start to drain the reservoir, and then as time progresses and our knowledge base increases, then we have a better ability to actually pull out all sort of the last drops out of the reservoir. So this is sort of our sort of approach to completions. So not sort of do you only have something for actually intervening, but actually we have a sort of preferred design also. And the design here actually came about because of sort of a need for high temperature, high pressure sort of well design. And high pressure well design, that puts even more sort of stress on sort of advanced jewelry in the ground, because obviously you're working with reliabilities of electronics, hydraulic equipment that's going to stay down there for many years. And once you're in this sort of high pressure, high temperature arena, then all that is of course under much more sort of stress. So we designed here actually a low capex well design, that actually is made smart by having sort of the full sort of flexibility and the full flexibility of actually being operated by robots sort of down the road. And of course the idea is that you can start your field development earlier. You have a lower capex, lower investment up front, and you have a higher, obviously your return on capital becomes much higher. And then your reservoir sort of characterization uncertainty, you mitigate by actually looking at it in the tail end and then adjust your well design as time progresses, where here, as you can see, you can add on multilaterals, you can add on, and you can actually start with one well design, and then as time progresses it can either become a multilateral well or it can be a fully control valve with multiple zones. You can inject assets, you can change it from being an oil producer into a gas injector, water injector, as time progresses. But upfront, you have a lower upfront capex, but you maintain your smartness in the system, because the robots down the road gives you the smartness you need to operate and do your data gathering. In the state-of-the-art system, we actually have a well intervention frequency of roughly sort of 18 months on sort of every well, and it means that we actually have updated data every 18 months, so they can update all the models sort of on a sort of residue sort of. It's not a high frequency sort of this point in time, but at least it's on a decent frequency, and you have to remember that sort of a reservoir, it might be drained over sort of 30, 40 year period. So even having updated data every sort of 1 year, every 2 years is not that bad. So the idea is that the drainage approach is fine-tuned over the lifespan of the reservoir. Historically, a lot of reservoirs has been sort of designed around sort of a production phase of maybe 3 to 5 years. Here, with the need for recovering more, you might, at least in our view, you might as well just realize that reservoirs will be producing for 10, 20, 30 years. And there will be issues with sand, scale, the whole lot. So the message here, change the intervention strategy. So you defer kind of your issues or your investments to later on, and actually avoid sort of upfront larger investments. And then routine interventions actually becomes a tool, a management tool for actually managing your reservoir, where you continuously monitor your reservoir and actually compare what's your model up against what is actually happening in real life. So that was it. Yeah, thank you.
Yeah, any questions, please?
Chris Mankini with OTM. Thank you very much. Very interesting. It's worth sort of setting the scene in terms of the. It isn't that people don't want to intervene in the subsea wells. It's just very expensive to do so, and perhaps the technology for subsea well intervention has just lagged the smart well intervention. The smart wells. So there's just maybe a lag in the technology there in terms of actually being able to get into the wells, rather than a lack of desire to intervene.
No, I agree. It's probably not been a lack of desire. And if you actually look at number of subsea wells, a lot of them have actually been a major sort of disappointment, because some of them have only been producing for 1 or 2 years, and then they died out. And then you're sitting there with sort of your calculator, kind of bring in a semi-submersible, sort of you start off with $20 million, and then you're supposed to do something, and then it'll probably cost you $30 million. And at drilling a new well, you need to have return on capital 6 times at least, so 30 times 6, so you are sort of at $200 million suddenly. So if you do an intervention, it better yield $200 million before either you won't touch it. And then you can calculate on your what's the likelihood of your intervention actually doing something right here, then add another sort of likelihood on top of that, and then of course you'll stay away from intervening. But here the idea is that if you change the cost picture completely, if you actually remove all the heavy components, remove the 200 guys on deck on the semi-submersible, remove the riser system, remove all the fluids that need to be pumped, remove the semi-submersible, the heavy capex and that. You don't need the towing equipment, you don't need the helicopter support. It's just a vessel in the Gulf of Mexico is actually just a supply boat. And you don't compromise on safety because there's no hydrocarbons to surface. You have triple safety barriers in place. You have the ability to cut any tool. You have the ability to abandon at any point in time. So no compromising on safety. But all the heavy components have disappeared and you're left with very few sort of expensive components but very small components.
Yeah. Anybody else? David, please. Yeah.
Yeah, just maybe my ignorance. I'm trying to work out in my mind how the E-line works in practice. I mean, how thick is it, and how do you get it? You're actually running it down with tools on the end of it, yes, inside the production casing.
Yes.
And if you're going to a horizontal well, you can push it along, or you've got a little tractor on the end that drags it along. How does
exactly.
It work?
Yep. Sort of you call the small robot, a small tractor device. Yeah, it drags it along. Right. The typical cable is about the size of my little finger.
Is that all?
Yeah, that's all. Yeah, and we go down to 10 kilometers of depth with that. It's tiny. A typical tractor consumes 1.5 kilowatts, equivalent to a small hairdryer. That's it. But with this power, we actually compete against the full-size semi-submersible with 10,000 power. That is true. Kind of. It really sounds completely silly and really.
Another question back there, please.
Hello. Have you carried out energy return on energy invested analysis? Because it sounds like a radically transformative technology.
The question was?
Some of the fields, I mean, it's common to talk in terms of gross flows of oil.
Yes.
What is less commonly discussed is the amount of energy required to produce a given amount of energy. For example, it used to be that in somewhere like Spindletop, 1 barrel of oil used to produce 100. Now that's collapsed down to 10 or 3 in some places. The potential of your technology, if what you're saying is in terms of the infrastructure disappearing, the energy return on energy invested number would dramatically increase. That's the side effect of the that's why you see a side effect of profitability.
You're completely right. And one of the things that, if you look at a lot of sort of platform installations, they're only built to handle, say it's that fuel. They handle 300,000 barrels of fluid per day. And they could either decide, okay, we'll take water cut up to 90%. And a lot of sort of oil fields that take water cut up to 90%. But then end up with a relatively little amount of sort of fluid that's worth anything, the oil heading back to surface, or heading back to shore. So if they instead of could look at each well, okay, and said each of them, if they start to produce water, they're contaminating my facility with water, means that I get less fluid production and less oil heading to shore. So that's sort of one way of looking at it. Another way of looking at it is that once you start producing unwanted sort of fluids, you will have scale issues in your production facilities at surface. And a lot of sort of oil companies have faced that they have redesigned, changed all their piping at surface because they had H2S issues, scaling issues, all sorts of issues in the topside facilities because they produce water. Here the idea is that keep the water in the reservoir. The production rate might look smaller, but it's actually oil you're producing, and the oil rates you're producing are actually higher because it is truly oil. Another thing is that it flows easier to surface. The need for artificial lift becomes much less once you have oil in your fluid column heading to surface, it has a tendency to flow by itself, or with a small help of, say, gas lift, where if you have a sort of solid water production of maybe 90%, you're consuming a lot of energy in your system just to be pumping fluid around, and you will actually have to pump it to surface also once the reservoir is sort of getting depleted. So of course there's a lot of sort of energy savings in this philosophy also.
My final question is, what is preventing a rapid uptake of this technology?
You can answer the question.
Yeah.
Well, I was just going to...
I try to sort of come with a polite sort of slide before kind of the industry was slightly slow, but we are sort of in most sort of areas around the world, and it's growing at a nice pace.
So you're obviously well connected with people like Statoil, and from what I understand, Statoil, in the well design, they almost have to have a justification for not using smart wells. Are they now coming round to the idea of the hybrid as you described?
It's actually, again, it's design, again sponsored by them.
Yeah.
It's for their new high-end stuff.
Yeah.
And what we realized once we began sort of designing it, that it was actually sort of something that actually had a much broader purpose, because the same design could actually be used in SAC-D applications for really high temperature application. It could be used in shale plays, where we can actually do cement assurance, same technology, just used for slightly different purposes. Making sure we don't get sort of groundwater contamination. We got zonal isolation here, again built because it's high temperature. Now then it suddenly becomes acid resistant also, and suddenly you can do all your fractures, and you can do a lot of things that you couldn't do in the past just because of all the limitations.
Okay. Well, thanks, Jørgen. I told you he started off with an idea, and you just heard what it is. And I remember the first time I saw one of Jørgen's systems, I mean, as he said, the wire was this thick, and the tractor was the size of the sort of map roll that you see people struggling around with, a dozen maps of the North Sea in, or something like that. It was just amazing. So thank you very much, sir. And